All right, we've started. Quiet down, quiet. Questions on the homework? Yeah.
We didn't have
We did not have homework.
We didn't have
That was like, that's messed up. It's not funny, but at the same time,
Could have gotten so much. Okay, we're going to do two more examples. Hey! Quiet. Okay, this is our third example. And the same question applies. We want to determine if it's competitive or not, and then we want to actually solve it qualitatively, perform qualitative analysis. So, what's the first thing?
Find if it is competitive or not. It is competitive.
How do we
I
know
mean,
it's
it's not
competitive?
competitive because N1 survived due to Lowe's method.
Well, sure, we can do Lowe's method,
Or
which would give us, what would it look like?
it was
There was an X here, and the arrow would point. Right, that's the smaller denominator, so the arrow would point up, and that's the smaller denominator, arrow would point up, which means what?
N1 N2 survives.
And 2. So by Lowe's method, we have boom, boom, and 2 survives. Not competitive. Or we could have done competition table. And in the solutions, I put both ways in case you like one more than the other. So what would go here?
The effect of species 1 on itself.
Yeah, which is
1 over 50.
1 over 50 here.
And species 1 on 2 is 1 over 100.
2 on 1.
2 on 1. Yeah.
1 over 25. 1 on 2.
1 over 100.
And 2 on 2.
1 over 100.
Okay, so which one of these are bigger?
These first one.
This one is bigger, right? So that already tells you not competitive, right? Because 1 is doing itself more damage than it's doing species 2. 1 does itself more damage. Than it does 2. Okay, so we can determine if that it's actually non-competitive or not competitive. And you can use either method, I don't particularly care. Okay, so now that we want to examine it, so the first question was to ask if it's competitive. The second one is to qualitative analysis. What is the first thing we need to do?
Let's find the SS.
We need to find the steady states. So what do we usually do here?
Well, you can choose one.
From equation 1, what do we have?
N is equal to 0, or N1.
So we have N1 equals 0,
Or 50 minus 2N. Or N1 is equal to.
or let's write this out, 1 minus N1 over 50 minus N2 over 25 equal to 0. So this means we have two situations, N1 equal to 0, or this I can multiply through by 50. I would get 50 minus 2N2 would give me N1. Right, so I have two situations, either N1 is 0 or N1 is this. And so I deal with one at a time, plugging into equation 2. Hopefully you copied down by now. N2 if n1 equals 0, we end up with
well, n2 can either be 0 or n2 can either be 100.
It was 1 minus n2 over 100 equals 0. So n2 is either 0 or n2 is 100. So what are the steady states here?
0, 0,
0, 0, and here we have 0, 100. If our n1 is actually equal to 50 minus 2n2, then I would plug it into the equation. We will have n2 times 1 minus n2 over 100 minus 50 minus 2n2 over 100 equals 0. Okay. So then n2 equals 0, or this equals 0. I can multiply through by 100. 100 minus n2 minus 50 plus 2n2 equals 0. So from this, 2n2 minus n2 is 1n2, and then I just have 50 here.
That's minus 50.
So n2 is minus 50. Right? So what is the other steady state here? If n2 is 0, n1 is?
It's 50.
Just plug it in there, you get 50. This would mean n1 is?
150.
Plug minus 50 into here. Yes, 150. So we have two other steady states, 50, comma 0, and 150, comma minus 50. So these are our four steady states. Then what do we do with them?
And the no line.
Can I get rid of this?
Yes.
So this is the n1 axis, that's the n2 axis. So where's the so what's the first line look like? N1 null line.
Well, we set the inside equal to 0, so the first line is equal to is at 0, 25, and then at 50, 0.
Okay. Yeah. So if you're in the first equation, if your n1 was 0, your n2 would be 25. Call that 25. And in the second one, if your n1, if your n2 is 0, your n1 is 50. So this is the n1 null point. And then we have that in the second equation, they're both 0, 100 on the axis. This is 100, and 100. And this will go like that. Not drawn to scale. This will actually cross it over here at some point at that minus 50. Right, where this will be at 150. Which doesn't leave much space down there, but okay. So what do we know? How do we start setting this up? I think I actually want to draw this better. This looks the target.
Don't like your work?
This is at 100, n2 axis, this is at 25, this is at 50, this is at 100. one axis. The 2550 was the N1 null line, and then this one was the N2 null line. This one is the N2. Okay, so what does the arrow thing look like up here?
Left and down.
Left and down. Which means over here, if I jump over this line,
Right and down.
right, I jumped over the N1 line, so the N1 arrow will change, which is the horizontal arrow, so that would be right and down. And then if I jump over here,
Up and right.
I just jumped over the N2, so the down will now goes up. If I jump over here,
Up and left.
I jumped over the N1 line, so then it stays up, but now it goes to the left. Yes? Which part? The arrow parts? Well, up here we know it's always this, based on how the equations are set up. Because we had 1 minus n1 over something minus n2 over something. So it's always 1 minus some big numbers, right? So it's always going to be negative for both the dn1 and dn2. So I know I'm decreasing in the horizontal direction and the vertical direction, so it's always this. Now what we do is, you have to remember that the n1 controls the horizontal. It's like your x value, which controls the horizontal. Your n2 is like the y, which controls the vertical. Right? So we drew one line for the n1, which was this guy, right? Which means every time I jumped over that line, I have to change the horizontal, right? This line was for the n2, that controls the vertical. Every time I jump over this line, I have to change the vertical. That's basically how it starts. So if I start like here, and I jump to this region, I actually jumped over the n1 line. Since n1 controls horizontal, this guy that was a left will now change to right, and I get this. Then I jump over here, which I just crossed the n2 line, so now my vertical is going to switch. It was down, but now it switches to up. Then I jump over here, and I cross this line, which is the n1 line, so now the horizontal is going to switch again. So instead of it was going right here, it will now go to the left. So it's like every time you jump over a line, you change the arrow corresponding to that line. So you change the horizontal ones when you jump over the n1 null line, you change the vertical ones when you jump over the n2 null line. And so the idea is that if I gave you something like starting here, it would look like that, and so on and so forth.
So then what do we say about that point, 0, 100?
Well, I'd have to give you an initial point, but what do you say?
Anywhere that you land, it will always go towards the n2, meaning that there will be 0 and 1. In which case we have 0,
Yeah,
100
like here.
as a solution.
Yeah, it depends. Yeah.
So that means that when the species
Like
level-
ultimately, this is where everything's gonna end up if you run it.
Okay. So it means when there's 0 of the n1 species, there will be about 100 of the n2 species?
Yeah. And if you start with non-zero populations, it'll eventually end up so that the n1s will all die out, and the n2 will sort of hover at 100, which is the carrying capacity of the n2. Okay. Questions? We're gonna do it again. Last example in this section. And basically for these problems, this is always sort of what you're going to want to do. I'm going to ask you whether it's competitive, and then you're going to have to do all this and eventually end up with graphs. 150, 125. Is it competitive?
Yes.
So we do that arrow thing, and so the arrow would go here, and then that arrow would go there. So by Low's method, you're in the depends case. If he's competitive, it's a bona fide competition. We don't know who's going to win. It depends on who gets the upper hand first. Competitive. Or I could do the table. I didn't fill in the total last time, but you don't really need it. So what goes here?
1 over 100.
1 over 50. 1 over
25.
25.
Over 100.
So notice that this one is bigger and that one is bigger.
So it depends.
So each species does the other more harm than it does itself, so it's competitive. Each species does more harm to the other than itself. This means competitive. So 2 ways to throw competitive. Let's talk about qualitative analysis. So we're going to find the steady states. Basically in 1, what do we do? And 1 equals 0, or 1 minus n1 over 100 minus n2 over 50 equals 0. Yeah, that's right. I can multiply by 100, that's the LCD. And so that would give me 100 minus 2n2 is equal to n1. So I have 2 situations, n1 is either 0 or n1 is that. And then I plug them into the second one. So now if n1 equals 0, equation 2 would become something like n2 times 1 minus n2 over 100. Is it over 100? Yes. So which means n2 is equal to 0 or n2 equals 100. In which case I have 2 steady states, 0, 0 or 0, 100. So these are 2 of my steady states. If my n1 was 100 minus 2n2, then when I plug it in, I would get n2 times 1 minus n2 over 100 minus 100 minus 2n2 over, I think it was 25. n2 equals 0, or all of this would be equal to 0. LCD is 100, so I can multiply through by that. I would have 100 minus n2 minus 4. Let's write it out. So here I would have 100 minus 400, so that's minus 300. Here I'd have minus n2 plus 8n2, right? So that's 7n2. And so n2 would be 300 over 7. This would mean n1 is equal to n2 I just plug into 0, so that's 100. So I get another steady state, 100 comma 0. Here, I would have n1 equals, I plug that in here, I would get 600 over 7. This is 700 over 7, so I just get 100 over, minus 100 over 7. Positive 100%. That's the, this is 700 over 7. And so that last steady state is 100 over 7, comma 300 over 7. And now we can start to graph stuff. It's the n1 axis, that's the n2 axis. What does the n1 null plane look like? Where are the intercepts? On the n1, we're going to intersect what? For the n1 null, when n2 is 0, n1 would be 100. And when n1 is 0, n2 would be 50. 50. So now I connect those two with a line. This is the n1 null prime. And then we move on to the n2 null prime. So my n2 would go through 100. And my n1 would go through 25. So it would connect those two. Now we're going to put in our arrows. Always that in the top right. This is the n2 null. If I jump over here, what happens?
Like that.
I passed over the n1, so my horizontal is going to change. And if I jump over here, my vertical is going to change. So it's going to go up and to the right. If I jump over here,
Left.
I jumped over the n1, so it's going to go like that. So those are my arrow diagrams. And so look at something like this. If I started somewhere like here, what would happen?
You're gonna go to the 0.
I would go here and then
Go
down.
to 0.
But what if I started somewhere like here? Then notice I go here, I pass here, but now this one will tell me to go that way. Right? So I have two different situations. I can have n1 dying out, or I can have n2 dying out. Or if I'm like right here, I could maybe even travel right to the middle where both survive. Right? Or if I start like here, I can go up and then that way. If I start here, I'll go up and then that way. Right? It depends on where I start.
So then you know that point has to be 100 over 7, comma 300.
This
over
point
7.
here, yes, is 100 over, is that way.
Okay. Anything below or down changes to.
So you said if it's in front of the 100 over 7, it goes to that point and they both survive?
Yeah.
So where's the competition then?
No, the competition means it depends on where you start. Like, we don't know the outcome. We don't know
So it's possible that
beforehand which species is stronger, which species would win. It's a competition that you have to watch how it plays out. And it really depends on your initial condition. If you start out where the N1 has a much larger population than the N2, then the N1 will win, right? They start with the upper hand. Right? There is the case, though, where your N1 is relatively small and your N2 is relatively large. You could end up with both surviving, right? So it's a really, you never know. So that's what makes it competition. Right? It's not obvious. It depends on where you start, right? And who's. Questions? So ready for a test on Wednesday?
On Monday.
No, Wednesday.
You said Wednesday.
Because Wednesday's for
You said
homework,
Monday.
not gonna play
You
this.
said Monday. You said, wait, Jhevon, I had a question.
I'm pretty sure I said.
Can you tell us the test grades for the
What? You have? I sent the report cards already.
You
Not
did.
to me and
He
Boss?
has it. See?
I
No,
got
he
it.
did, he did.
See?
You said this so your favorite
See?
student, the rest of us are sitting
See?
here with.
But
without.
It doesn't say your grade, right? You gotta press back
oh, I see.
and then press grades.
It should show everything that I have for you so far.
Does everybody have an individual link or can I follow?
No, everyone gets a link sent to their.
Mine says something.
Yeah, me and Boss are sitting here without grades. That means we got all.
If what? I'll look at it. Ask me these questions after class. Questions on this.
Oh, I don't understand it.
Yeah?
We don't need to write like after you make the entire graph like a conclusion sentence. If initial condition is this, then it will head towards the end.
I might ask you that, yeah. So in like a question, I would actually give you one of these to start at. I might say, start where N1 is 90 and N2 is 25. And then tell me the long-term behavior. And then by looking at this picture, you'd say, oh, N1 would likely be the one that survives and N2 dies. Right? So yeah. So a question would only have one of these curves. It just depends on the initial conditions that I gave you. Which, like in the quiz, I actually gave you an initial condition. It's going to be very similar. So, any other questions?
We have a test on Monday?
Yes, Monday. Monday, you said
No, you said Monday, right?
You said Monday.
Because you said Wednesday was gonna be for the homework.
I said Wednesday or Monday, didn't I?
No, you said Wednesday was review and homework.
We all agreed upon Monday.
Friday. Stop lying to us.
It's the final word.
He thinks it's funny.
Okay, let's move on.
Wait, I need to know.
What?
I need to know.
Monday.
It's Monday.
Okay.
So on Wednesday, finish the homework for chapter 6. You can ask me questions on chapter 6, and I'll also set aside some time for review.
Very cool.
So, for the example of the date, starting from the chapter.
It's in the syllabus. It's everything that's in the syllabus.
4, 5, 6.
4, 5, 6. Okay, so if there are no more questions, that's the plan. So now with chapter 7, we're going to start to move into a different area of our syllabus. Statistics! Yes!
I'm gonna go drop this class.
What? Why? Statistics, the fun is just starting though.
You call it fun, I call it
I had a
mind-numbingly
statistic
sad.
today for my class, and I failed it. So bad.
So you have familiarity with statistics. That seems better.
That's called failing.
We're going to call it descriptive statistics. That's the name of the chapter. So let's see in chapter 7, we're actually going to be doing statistics for a few chapters. Chapter 7 is really long. Okay. In chapter 7, we will focus on what we're going to call univariate data. So this means focusing on one data set. Represented by one variable. So basically we're looking at just one set of data about one thing. That's chapter 7. In chapter 8, we're going to actually start looking at several things at a time. So let's start out by looking at some definitions here. What is statistics? Good question. What is it?
It's used to interpret data.
Yeah, so one definition is the study, analysis, and interpretation. Data. So we look at, well, I gave a more general definition here. I wrote the science of collecting, organizing, displaying, and analyzing data. Basically the same thing. Okay. Two can actually refer to the actual data being studied. Right? Like baseball statistics, it's like used as a noun there. Right, so those are two ideas for statistics. Definition, I talk about descriptive statistics. The title of this chapter, what is it about? Descriptive. This is the science of, yes, qualitatively describing the main features of a data set. Why is that important? Why do we care? Why should we care?
Oh, I know this.
Okay.
On Monday we have a test. No.
Okay, so why is it important?
Because sometimes when you get like scientific data, their trends aren't completely apparent. So you could tell if there's a correlation, which is a type of statistical analysis, or there's correlation coefficient, chi-squared test. So you could tell a relationship between two separate groups.
Why would we want to do that?
Like let's say you want to know if smoking leads to bad lungs.
Okay.
You take a group of people, like you take a bunch of people and you find out if they smoke and how their lungs are, and then you want to see the relationship between them. But you can't just look at all this data and figure it out. You gotta, do that stuff.
Yeah.
Some math in there.
That's actually a pretty good answer. You were worried about statistics. Yeah. Why is it important? It helps us to answer.
Thank you. I sign autographs. Hit me up on AIM.
Important questions through the data. Right? So, does smoking cause cancer, right? That's a question that we can answer using statistics. Right? That's an example, right? There are questions that we have about the world, and sometimes the way to figure it out is through statistics. You collect a large body of data examining things affected by the thing you want to study, and then you sort of make conclusions about it. Right? Does smoking cause cancer? Does living in a city reduce lifespan?
It does.
I don't know. Does it? We'd have to look at the statistics.
I can move into the city and see all that faster. This policy has to really discuss.
Anyone pass Jhevon's class, right? These are all questions that we can answer with statistics.
That's actually a really
So you
good
can look at Jhevon's grade book. Does anyone actually pass this thing? Let's look at the statistics. Does Jhevon curve? You can look at the statistics for
Does
that.
Jhevon curve? That's a very good question.
That is a good question. We should wait until the end of the semester to find out. I think it will take a lot of studying, in-depth study. Right? So basically, that's why stats is important. We're collecting data not just because we want to collect data. There's a question that we want to answer. And we don't have a clear way to answer it, so we collect a lot of data. Right? The idea is, usually groups of things behave quite similar. And so, for example, by finding out how most human beings would react to something, you can kind of predict, well, most likely this will happen to you in this situation. Right? So that's why statistics are important. Okay, so...
Can I tell you a statistic story? It's funny. Never mind, continue teaching. It's chunky and good this time. It's really good color.
Maybe later. Okay, so this is why statistics is important. Statistics is the science of collecting and analyzing data. Ultimately, the goal is we want to be able to answer some sort of question, right? And so what we do is we sort of have to analyze the data somehow. But then, for example, having just a lot of numbers doesn't really help anyone, right? So we have to come up with ways to organize this data, right? And so that's what descriptive statistics is about. We're describing the statistics that we've collected, right? And we want to do it in some sort of meaningful way, right?
Mean, median, goal.
Those are some ways. Let's look at,
What do you mean no one goes statistic class? No, 3 words.
we would like to describe the data. In a meaningful way, right? Like someone should be able to look at your data and be able to tell something about it by the way you describe it. Right? So what are some meaningful ways? Let's one way is called a frequency table. This is one way to analyze data that gives you some information, right? So say you have 15 grades in a class, right? I'm not saying it's Jhevon's class, someone's class. First grade, F.
It's Jhevon.
I just thought I'd start with that one, and that was, yeah. A, B, B, C, D, C, C, F.
This is
A,
definitely
A.
Jhevon's class. Too many A's.
Yeah, that's not very realistic. A, B, C, D, F.
He got a lot of Asians in the class. He got,
See, this is why I can't allow you to tell jokes. This is why.
your friend Lo. The Asian one.
Is that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, let's say you have 15 grades, right? I just give you a list of letters. What does that mean to you, right? It could be like a bio class where there are 200 letters. I give you just a string of 200 letters, okay? Right? It's not very useful to me. The data is not very accessible. So what we can want to do is we can organize this into a frequency table. Organizing data is a part of statistics. So I can look at something like this. I can look like grade. And then I can put frequency, the number of times that grade shows up. So I can have an A, B, C, D, F. And these should all add up to a certain total. So how many A's are there?
3.
When I count them off, there are 3 A's. How many B's?
3.
There are also 3 B's.
There's 3 Asians there. 3 Asians.
Oh,
4 C's. How many D's?
2.
How many F's?
3.
And does that actually add up? This is 3, 6, 9, and then
Yes,
6.
it does.
So that adds up to 15. Okay. Now think of the difference of seeing this and seeing that. Right away I can sort of get a better picture of how this class is doing, right? I can know, for example, more people get C's than got A's, right? More people got F's than got D's, right? So I can look right at the data and I can immediately answer some questions about it, as opposed to you give me this long string of letters and I have to like count myself. It's going to take forever. By the way, 15 data points is nothing. I mean, if you're actually studying statistics in the real world, you're going to be looking at thousands upon thousands of data points, right? But this is just an example, right? It's a lot nicer to, instead of giving me a list of data, put it in a table. Tell me how many of these things there are. That's one way to organize the data so I can actually answer some questions about it. And of course, the total here should add up to the total number of data points, so you can always double check yourself. Okay, so a frequency table is one way to organize data. Sometimes we want to analyze data in terms of percentage or proportion. Or like chance, which when we get to probability, we're going to talk more about that. And so for this, we use what we call relative frequency. Okay? So yeah, I know that 3 people got A's, but what percentage of the class is that? Right? I can ask that person. Right? So I can do something like this. So I can have here the grades, A, B, C, D, F. I have the frequency, which I just had before, which was 3, 3, 4, 2, 3. That would add up to 15 total. And I can have what I call the relative frequency. How do we compute relative frequency?
Over the population.
Right, I want to find a percentage, so what am I going to do?
Number of the total times.
Yeah, the particular data point frequency over the total frequency. Right, so this would be 3 over 15.
20%.
That's 20%. So this would be 3 over 15. which is again 20%. 4 over 15 is what?
26.67%.
27%.
26.67%.
Yeah, I wrote 26.67. 26.67%. I can have 2 over 15, which is 13.33. And the 3 over 15 is again 20%. You can add up all the percentages, you should get roughly 100%. Very close to it. Sometimes rounding error will get you off from that, but you shouldn't go too far from 100. I'm going to add something else here. Let's talk about what we call cumulative frequency.
So you add the percentage of the previous.
You keep adding frequencies of everyone at that level and above. So pretty much at this point with the A's, our frequency is 3.
And 6.
And at B, it will be 3 for B plus the 3 that came before. So there's a 6. For C, it would be that 3 plus the 3 plus now 4, which is 10. And this would be that 3 plus the 3 plus the 4 plus the 2, which is 12. Then that would be a 3 plus a 3 plus a 4 plus a 2 plus a 3, which gives me 15 ultimately. Right? So cumulative frequency comes in handy when we want to analyze how many data points are at some level or better. Right? So again, statistics is we collect the data, but we want to answer some questions about it, right? So I give you a string of data, not very useful to you. So you might throw it in a frequency table. You can tell me how many data points will end up in a certain region. But then you might want to talk about in terms of percentages or a chance. So I can throw in a relative frequency, where I can divide by the total, and I can get a percentage chance of something happening. Then I can talk about cumulative frequency. Now this allows me to answer a different question. I can say, how many people got C's or better, right? How many people got D's or better, right? I can ask how many people passed, right? So if you don't need this course as a prerequisite, a D is good enough for a pass, and so I can say, well, 12 out of the 15 people would pass this class, right? I can see how many people did better than C's, 10 people, right? I can just immediately tell you how many people will be at a certain level or better, right? And I can say it right away because I've just organized it in a table. Everything's nice and neat, it's right there. And it makes use of the data. It makes it far more accessible to answering questions, which ultimately is the whole point. I want to be able to answer questions, right? So I don't just need a string of grades. Tell me how many were A's, what percentage were A's, how many people got C's or better, right? These are all questions I could ask about this data, and organizing it in a table makes it easier to answer those questions. Right? Did you guys finish writing it? We need to write fast.
How is this qualitative?
Huh?
How is this qualitative?
What do you mean?
You said this is a qualitative science.
Yeah, well, we're going to go to more qualitative things. This technically is kind of qualitative, it's a table. But from this, we are, of course, are going to, we're going to move into qualitative. Right, this is how it starts, right? This will just show you how to organize things, but ultimately we're going to start drawing pictures from this. So that's where the qualitative is. Coming up soon. What?
What does it say after or at some?
So it's cumulative frequency. Comes in handy.
Yeah, we know that.
when we want to analyze how many data points are at some level
Okay.
or better. Right, so tell me how many people are here or better. And of course, better is in quotes. I mean, if we're talking about lung cancer, better is probably relative. Okay. So this is the idea. This is where it all started. Statistics was rough. We wanted to organize this data so that we can answer questions about it. So we can start to throw things in a table. But it won't take you long to realize that tables can become cumbersome. Right? If I'm looking at thousands of data points, I give you a table with 1,000 rows in it and 6 columns. It starts to get daunting after a while. So eventually we start to use pictures, because everyone loves pictures. By pictures I mean charts, graphs, etc. So pictures are really nice. They're not super quantitative, but they allow us to identify key areas in our data that we might want to pay more attention to. So if we're looking at a bar chart, somewhere where there's a spike might be something to pay more attention to. So I'll look at the graph, I'll see a bar that's super high more than all the others, and then I'll only look in the table for that level if I wanted to find more information. Right? So we can talk about graphs. So examples of some graphs, which we will be drawing in this class, so if you pay attention to it, is a bar chart. This is for qualitative data. Right, there's another thing called a histogram, which you usually use for quantitative data. That's for qualitative data. Example, grades. It's a kind of qualitative data. This plots data against very usually we'll plot it against relative frequency. Or sometimes just regular old frequency, but that's less typical. Very usually in a bar chart you're going to plot against relative frequency. Okay, so actually let's look at the graph for this guy. Let's talk about the bar chart. So now I can talk about a bar chart. We're still looking at this data set showing the distribution of grades. So what we would do is do this, and I can put the grades on the horizontal, A, B, C, D, F. So this is the grades. And on this, the vertical axis, I'm going to put the frequency, or the relative frequency. So I would have a 13.3%. I would have 20%. And I can have 26.7%. So my A would be where at the 20. So I can draw a bar going up to the 20. My B is actually at the same level, so that's also 20. My C is a little higher, that's the guy that's at 26. My D would be at the 13. And my F would be at 20. Before I discuss what this graph looks like, I just want to point out some key features. Title. Always title your graphs. Axis labels. You should always label your axes. I should know what your horizontal, what you're measuring on the horizontal, what you're measuring on the vertical. Note for bar chart, there are spaces between the bars. For other data, such as like histograms, there are no spaces, right? So this would be a bar chart. It has a title saying a bar chart showing me what, right? It shows me how these things are being measured. I can say relative frequency or frequency here. Very usually it's relative frequency. But now we can answer different sort of questions about this. Like, if I didn't even know the numbers, I could look at this and I can say, oh, the same amount of people got A's, B's, and F's, right? D is by far the least frequent grade. C is the most frequent grade, right? There's some questions, some qualitative questions I can answer just by looking at this picture. And if anything stands out to me, like, wow, C is the most frequent grade. I wonder how many people got C's. I can go to this table and look up that row. Oh, 10 people got C's. Right? How much of the class was that? 26.67%. Right? There's a lot of information that we can answer from this data, right? So we can go from a list of data that wasn't very useful to anyone, throw it in a table where it can answer all sorts of questions about frequency and percentage and cumulative, and then we might say, oh, the table is getting too big, it's too cumbersome, then we do a picture. And then we can just look at the picture and just talk about the data, right? How the data is behaving. We can see trends. We can see spikes. What is the most typical value? We can see all sorts of things. And if ever we need to analyze it further, we can of course go to another way. But this gives us a really nice way to segue into the study of the data, right? So that provides another way to organize data, very qualitatively. And so a good chart will have title, axis labels, and it's not necessary here, but it should have a legend if applicable. I don't think I'll ask you to draw anything by hand that you'll need a legend for, but just be aware. You might have stuff in your Excel homework that you need legends for. So that's a bar chart. Very important chart. More than likely you have to draw it one at some point. And it allows us to represent data in a very accessible way. Okay. Another kind of important chart that we're going to want to look at a very typical one is the histogram. Well, histograms, I should say, usually represents quantitative data. Right? So numerical data is what you want to use a histogram for. Right? So if you have the choice, like if someone asks you about grades they gave you as A, B, C's, you would use a bar chart to represent that data set. If someone actually gave you numerical grades, you would use a histogram to represent that data set. This is the convention for them. So this uses quantitative. So you're presenting quantitative data in a very qualitative way. You get a histogram. So let's talk about the features of a histogram. Histograms will often use what we call bins. Bins are intervals of numbers. Intervals of numbers. Representing a range of data sets, range of data points. You'd be surprised at how useful these things are. Let me show you an example of where you might use a histogram. Let's look at grades again. Okay, so here's the list of grades. We're going to have 20 of them. Here are the grades of 20 students. 57, 73, 81, 62, 82, 93, 51, 77, 72, 72, 54, 65, 78, 61, 70, 85, 62, 68. See, it's already annoying to 69. Yeah, these are the grades on the test. Okay, this is we have more students than this.
You use the first one.
Okay. Yeah, you don't want to see the rest of them. So I'm going to want to group these by tens, starting at 50. Right, so let's see an example of what a table that we're going to use to draw a histogram would look like. Grade, frequency, relative frequency. So now the grades, I don't want to like have a 20 data points separately, right? It's okay to group these. So I might say something like, I'm grouping all the grades from 50 to 60.
60 to 70.
You
Well,
mean
61 to 70.
50 to 50?
61.
And then 60 to 70.
Oh.
And then 70 to 80. And then 80 to 90. And then 90 to 100.
That one person. That's okay.
Yeah, that's true. That's good for them.
There's going to be a total.
They're cool.
Right? So sometimes you're given numerical data, millions of data points, thousands of data points. To make it manageable, you group them, right? You take some interval that you're comfortable with. You want to group them in all these intervals. So what we're going to do now is we're going to count the frequency with which numbers fall into each of these intervals.
Jhevon,
Yes?
when you're writing the interval, for example, you have 50 to 60, would you not want to start on 61?
No, they overlap.
It's
The bracket
parentheses.
No, the brackets means the numbers included in my interval. The parentheses means it's not. So 61 would actually fall in here. Yeah, so the kind of brackets I use for the bins is very indicative.
But where is
So
60
it'd be like
fall?
59.99.
60 would be here,
Oh, okay.
because it's included. It's a closed bracket.
Okay, so
Okay.
the first one is.
So now I'm going to count everything that's greater than or equal to 50, but less than 60. So what do we have?
3, and then it's 4,
1, 2,
and then the 54.
3.
That's it.
Yep, I counted 3.
3 over 20.
It turns out that this was 3 over 20, which was 0.15, so that's 15%.
4, the next one.
Let me just jump in. I actually counted these. So it turns out there were 6 here,
I'm so stupid.
and this was 0.3. There were 5 here, which is
No, it's
0.25.
See, I'm not stupid.
There were 4 here,
But I'm not stupid.
which is 0.2. There were 2 here, which is 0.1, and the total was 20.
Wait, I believe from the 60 to 70.
Yeah, there's only 4. I'm stupid, but I'm not that stupid.
No, 6.
1, 2, 3,
What? Who are we counting?
5. Oh no, now there's. Oh, okay, never mind. He's right.
Remember, I'm including the 70, but not the 80.
Yeah, I did it to the 68 and 69, so I thought there were only 4. Never mind, I am not stupid. Let's move on.
Okay. All right, so this is an example of a table using bins. I'm given tons of numerical data, very sloppily given. I organize into bins using ranges of grades, which we'd probably use anyway. This would be like A's or whatever. And so now I organize those into a table. These guys here are called the bins. Those are what the bins are. Right, these guys are called bins. They're really just the intervals that talk
I
about.
thought relative frequency was supposed to be a percent.
Percent written in decimal is the same thing. It's equivalent, right? So this is 50%, 30%. You can write it as a decimal. It's not a. There's no difference. Let's actually do a histogram.
Not confused by the other.
Just I'm gonna write slowly. Histogram. Histogram showing the distribution of grades. Right, so there's my title. You should always have a title. And we're going to, it starts out looking very much like a bar chart, except here on the horizontal, we're putting the bins, which is 50 to 60, 60 to 70, 70 to 80, 80 to 90, 90 to 100. So these are grades here. You have to label the axes. Grades. Here I'm going to put relative frequency. And so we have 0.1, 0.2. Sorry. 0.1. 2, 0.25, 0.3. I have a 0.15, 0.15. Okay. So in the 50 to 60, we have 0.15. So that's that bar. In the 60 to 70, we have 6, which goes up to 30. In the 70 to 80, we have 5, which is 25%. So here. In the 80 to 90, we have 20%. In the 90 to 100, we have 10%. So now, features of this guy. Notice there's no space between the bars. Bins organize in increasing order. Again, we have a title. And we have axis labels. And these make up a histogram. And again, we can answer all sorts of questions just by looking at this picture. We will, I guess, stop there.
So we,
The one thing I should mention is that sometimes we can label the bins by the middle number. It's the convention that you might see. So instead of writing the bin 5060, I just might write the number 55. And then write the number here 65, and so on and so forth. But it'll be right in the middle of the bin. It still assumes that there's a range going on. We'll stop there, continue on Wednesday, and we'll go over the homework and questions about the test.
So you're gonna give this back to class? That's on my cup. Look at it. I think he's gonna give this back to
Just email me first.
yeah.
he's not. Jhevon, are we getting the first test back first? Okay.
Yeah. Yeah, if you didn't get the email of the report, just email me and remind me, and I'll double check. I'll make